Hi, if you've been watching my channel lately, you've probably been seeing I've been doing a lot of PC-based retro computing projects using x86 projects like the old IBM XT. This is my current retro XT build using Sergei Kiselev's Micro 8088, as well as a bunch of other boards, compact flash board, floppy board, VGA board, parallel port board. So I've been doing a lot of development on this. I do have a KVM, can you see that thing? A KVM IP switch. So that puts the console, the VGA video, and the keyboard on an Ethernet connection so I can go over to my PC at the desk and program away on this. But there's a lot of times when I still need to copy files back and forth, and my go-to method for that has been to reach back here, pull out the compact flash card, plug it into my modern PC, copy the files on it, put the compact flash card back in, reboot. Shuttling this flash card back and forth, that's really, it gets old really quick. It could be worse. I mean, I could be using, like we actually did back in the day, a floppy disk. That'd be really time consuming. So I set out to come up with some way that I could share a file system between this computer and my high-powered Windows machine over there on my desktop, just to facilitate retro programming. Now there's several options you have to do that. So back in the day we had, terminal programs. You could X modem or Z modem files back and forth. There's something called LapLink. You could use that to transfer files. I think the XT IDE actually has like a serial floppy support in it. I've never tried that. You can get a network adapter. So on a PC as old as this, the 4 to 8 megahertz x86 range, I don't know how viable it would be to actually use an Ethernet network. I don't know if this machine's capable of doing it. It's kind of hard to find 8-bit compatible network cards. So I set out to come up with something else, and what I wanted to do was let's see if I can just share a file system between this and a Linux box like a Raspberry Pi. Okay, so let's say we have two machines. We have on this side, we have old ISA PC. On this side we have new Raspberry Pi. How to make this one talk to this one? Well, there's several options. You could do serial. I mean, we could set up an I/O port between them and send parallel across the I/O port. So what I figured I'd do this time, and this is the first time I'm going to try doing this because it's an approach I've not done before, is to use shared memory. So shared memory, 1 kilobyte. That's not much memory, but we can split that up. And down here we'll 512 bytes. Sector, buffer, and up here we can put a request. Reply. So inside this shared memory, our old ISA PC will go over here. It'll say read cylinder 1 head 1 sector 7. That request will go over to our Raspberry Pi. Raspberry Pi will have a floppy image. So it'll go down here and it will read, and then back will come the data. The Raspberry Pi will copy data down there. Now let's say the data is hello world. And then it'll say okay. Our ISA PC will get back the reply, okay, and then it will read the hello world. That's just a standard approach of two machines using a shared buffer between them. And then we'll, the next block of the file will send, cylinder 1, head 1, sector 8. Go over there, we'll go fetch it, come back, write the data, the reply, and back to the PC, and we just repeat this, treating this as if it was just a plain ordinary disk drive. So let's see what kind of IC we could use for this. So I looked on DigiKey for dual port static RAMs. What I came up with was this IDT 7130. This is a current production chip, so you can actually buy them. You don't have to go to eBay to find this thing. It's they're still making them, at least for a little bit longer. It's 1 kilobyte, and it has 2 buses. So you can see there is a left side bus and a right side bus. So we'll hook up our PC to the left side bus. We'll hook up our Raspberry Pi to the right side bus. The PC can read and write memory through the left side. The Raspberry Pi can read and write memory through the right side. Both of them can simultaneously use that RAM chip. So one complication we're going to run into is this is a 5-volt memory, where our Raspberry Pi is a 3.3 volt device. So the way the logic levels on the Pi are designed, and the way the chip is designed, if you send a logical high on the Raspberry Pi, that is high enough voltage to register as a logical high on the chip. You send a low, it'll read a low, but the problem is when the chip goes to communicate back to the Raspberry Pi. I measured this chip, I got out my voltmeter, and it's putting a high voltage out of 4.6 volts. 4.6 volts into our 3.3 volt Pi is pretty dangerous. It could destroy the Raspberry Pi. So there are some common approaches to this. Sometimes people throw a resistor in as a quick and dirty hack. You put the resistor in, it'll current limit. The Pi would have a protection diode. And then the current would get shunted through the protection diode. It will only flow enough current due to the resistor, so it wouldn't burn anything out. That doesn't seem like a very robust solution. So what I decided to do was to go with a voltage level translation approach. And I got this idea from someone on the Vintage Computer Forum. They were talking about a project they did, and they needed to translate voltages. So I said, what IC did you use to do that? And they told me they used a 74CBTD 3861. So I went off and I bought some of those. The 74CBDT 3861 is a 10-bit FET bus switch with level shifting. So these FET bus switches, I've never used one before. It seems kind of like magic to me. Here's a diagram of what's actually implemented inside the thing. So there's a buffer here that an enable comes in. The enable will switch on all these transistors, which will connect our A lines to our B lines in the bus switch, connecting 2 different buses together. It says here on the datasheet that this will look electrically like a 5 ohm resistor. That's great. This thing includes a built-in dropping diode that will automatically handle the level shift between 5 volt and 3.3 volt logic. So this seems like exactly what we need. It is a surface mount part. I try to avoid surface mount parts in my retro projects, but I couldn't find one in a through hole, so this seems like a necessary evil. So let's take a look at the schematic. There's actually not a whole lot to this circuit. So over here we have our ISA bus. As is typical of lots of my boards, I include pin headers so I can get to those ISA pins with test leads and such. Over here we have our Raspberry Pi. This is the B+, the 2 and the 3 model. It's got lots of GPIO pins. To take a lot of GPIO pins to make this work. Over here we have some addressing logic. That'd be this section. So we want to take our shared memory and we want to put it at a certain address on the ISA bus. So just like I did with the EMS and flash drive bus, you have something here that decodes the high address lines, what is it, like A12 through A19. So it generates a chip select, so that will allow us to put this shared memory wherever we want it in RAM. I usually put it at E000:0000. That seems to be a good address that I've used in my EMS boards and such. And then over here we have the dual port RAM. And you can see it's lined up with the left side and the right side. So the left side, these addressing bits, ISA data bits, mem read, mem write, and the chip select are all going over here to the ISA bus. The right side is all going over to the Pi. The address lines, A0 through, was it A9, we can hook those up directly to the Pi. So chip enable, write, read, those can all go directly to the Pi because those are simply outputs from the Pi driving the chip. The data bits we're going to run through the FET bus switch, that chip we just discussed. So that all the data bits are going to be buffered. The chip is, it's got an output enabled, so it's simply enabled all the time. It's hooked up to 5 volt, but it has that internal dropping diode to make it 3.3 volt compliant. And then on this side, these hook up to our Raspberry Pi. So it's very much just taking this dual port memory, slicing it down the center, hooking one port to the ISA bus, hooking the other port to the Raspberry Pi through the level shifter. You can ignore this stuff over here. That was me trying to leave enough room on the board that if I wanted to try to hack this out with some resistors instead of the FET switch, I could do so. Decided it just wasn't going to be safe to try that. I also added a couple open collector transistors. The idea here is that I would take a couple lines from the Raspberry Pi, run them to transistors. We could use that as like a reset switch and maybe something else like a power switch. There's times when you've crashed your PC to the point where Control-Alt-Del won't work anymore. If you're working over a KVM IP switch, you can't really run across the room and push the reset button every time you lock up the machine. So add a transistor there and we could actually do a hardware reset of the ISA machine. What else is on here? So I did put a jumper on the Pi so that you can decouple the Pi's power from the ISA bus. You could do that, for example, if you wanted your Pi powered on all the time. You could power up your Pi from 5 volts and not care whether the PC is powered. So let's take a look at the board I came up with. Right here it is. It's soldered together. This board I had fabricated at JLC PCB. If you watched my recent JLC PCB review video, this was what I called the green board. It was my $2 prototype. As such, I kind of hacked this thing up to make it fit within 100 millimeter width, so it's a little bit short. This 9-pin pad over here, that's so there's just enough room on there to put a DB9, and then you could mount a DB9 bracket like this one here. Mount it there, and you'd have a bracket on the card. There's just not enough room to mount. There's just not enough room in 100 millimeters to mount the mounting holes for a traditional bracket. It'd come out about here, and the mounting holes would miss the edge of the board. But a DB9 makes a nice way to mount a board that's a little bit short. So looking at the components on the board, here is the dual ported memory. If that looks a little bit big, that's not surprising. This is actually a 48-pin chip, not a 40. So it's a little bit longer than a standard 40-pin DIP package you might be used to. There's the jumpers for setting the address of the shared memory on the PC's bus. I have it jumpered currently for E000. Here is the 74 HCT688 address comparator that compares the DIP switches to the address pins and generates the chip select, pull-up resistors for the DIP switch. Here's the surface mount package for that FET bus switch. Down here there's a jumper that turns the board on and off. I started doing that with some of my newer boards. It's convenient rather than plugging something in and out, just be able to hook a switch up to it and I could just switch it off from the front panel. There's a couple headers here that hook up to those transistors. I have this one populated. I use that one as my hardware reset switch. Here is the jumper that supplies the 5 volts to the Raspberry Pi, and then here is the Raspberry Pi header. Now as far as hooking up your Raspberry Pi, there's a couple options. What I did for development, see, can you see this? Yeah, you can kind of see it. So a Raspberry Pi, and this is a 40-pin, like an IDE cable. It kind of fits the GPIO connector, and then you can take and you can, just plug it into there. Leave this monstrosity hanging out the side of the case. But my real intent with this board was to use one of these new Pi Zero Ws. So you just plug that on. So there we have it. The Pi 0W is mounted to the board. It makes a nice compact assembly. There's no junk hanging off of it, no cables, no nothing. See, it's not all that thick. We could easily fit this in one of our ISA slots. And we will put the machine together and try it out. Okay, so on the left we have a KVM IP switch that's hooked up to my retro computer. That allows me to interact with it over screen and keyboard on my modern PC. On the right we have Raspberry Pi terminal session logged into the Raspberry Pi. So I'm going to start by rebooting this just so we have clean boot. So there we go. Now it's currently booted off of my compact flash, XT IDE. There's no disk in the A drive, so if we do dir A:, it's going to fail because A is actually a physical floppy and there's no disk in it. So what we want to do is we want to run the PyDrive command. So that's going to install the BIOS driver. It's going to take over the A drive and start communicating with the Pi. So running that, frame segment, that's where the dual port memory is. So it saved the interrupt 13 handler and replaced it with its own. Now over here, I'm going to run the Python side of this on the Raspberry Pi, which is going to start serving up 1.44 megabyte image. And this D0 here says it's going to serve it up on disk 0. That will be the A drive. So that's ready to go. Now if we do a dir A:, we can see that it's reading this drive from the Raspberry Pi. So you can see here's all the reads it did to read the various disk sectors. This is Champions of Kryn. If we run start, it'll actually run it. Let drive A and then run start. There we go. You see there it loaded a whole bunch of program stuff. Lost video while it's switching video modes. And there we go. And then we could go into demo mode, loading game data and stuff. And there we go, that's Champions of Kryn. Let me exit. I never know exactly how to exit this thing. Anyway, I don't know how to actually exit it, but let's just reboot again. And here we are back at the DOS prompt. So drive A again, because we rebooted, it's reverted back to the physical floppy. Run PyDrive. And we've got our Champions of Kryn disk. Okay, so another thing we can do is we can actually change the image that's being hosted while the PC is running. So let me control break this. I've got a DOS 6.22 image. Let me do that one. Now, if we look at drive A, different stuff. You know, it's clearly DOS, a newer version because it's got QBasic and Xcopy and that kind of stuff. So that's great. You know, if you want to switch disks while the PC's running, you can do that. I'm also going to show you how to format and how to make a new disk. It's easy enough to do that. Let's go into the images directory. 0 equals work disk. 502 byte blocks. Let's call this workdisk.img. Okay, so I've made a blank file. Let's go here. We'll do workdisk.img. I'm also going to do unbuffered, because we're going to try to mount the image, do some fancy stuff in a moment. Okay, so we've got that disk mounted. If we do dir a : general failure, he's all messed up. I mean, it's just it's an empty disk, so obviously we can't read it, but we can format just like a real floppy. We can format it. So what it's done is it's written all of the FAT table and directories and stuff like that, and transferred the operating system to it. So dir a : blank disk with command.com. So because we are hosting this disk from the Linux machine, let's see if we can actually live mount that file system and alter it. Actually made a script for that called mount workdisk.sh. So what that does is it runs these three commands, creates a directory, sets up a loopback, and then mounts the image file as /mnt/ms-dos. So ms-dos. You can see it's got a command.com, an io.sys, and ms-dos.sys. All the stuff that ought to be there on a freshly formatted disk with operating system. I'm going to go into bash here for a second. Scott was here. ms-dos scott.txt. So let's just write a file on the mounted image from the Linux box, see if it shows up on the ISA machine. Did not show up. So I actually knew that was going to happen, because what we have to do is we have to type sync. So this is going to flush file system buffers, make sure Linux state is flush to that disk image. Now, dir a : scott.txt is there. Scott was here. So, I mean, this is going to be really handy for me, I think, to be able to just put files onto my retro computer using the Linux box. Won't have to cart disks back and forth. You do have to be a little bit careful mounting the same image on two different machines. You know, like here I did have to type this sync. If you were actually writing things here while we were writing things here, we could corrupt the file system. So it's kind of a use at your own risk situation. If you wanted to be really careful, you would stop serving it and then write to it on the Raspberry Pi. Then you would unmount it from the Raspberry Pi, then start serving it. You know, make sure there was no chance that it could get corrupted by being simultaneously written. Or you can live dangerously like this and write to the file system while it's in use and hope nothing goes bad. Well, I've also written this as a BIOS extension. So far, BIOS. At this point, we've always been running that pydrive.com file. The driver is also it's small enough, and the 1K shared memory is big enough that we could actually put the driver inside of the shared memory. Then it'll actually be there when we boot. So I'm going to add this -- BIOS option, and then let's reboot my machine. So you're not actually seeing any messages printed about the driver, you know, like it did when I ran pydrive.com. It printed out some text that said, you know, it's loaded and such. There just wasn't enough room to actually put those text strings inside the BIOS extension and get it inside of that 1K ROM. So I left out all of the text messages, but if we look dir a : it's actually there and working. Now, as a BIOS extension, we could actually boot from it. So I'm going to walk over to the computer, and I'm going to disconnect my compact flash. Just a moment while I do that. So my XT IDE is currently disabled. If we boot up, there won't be any XTID ROM, there won't be any C drive, but we should be able to boot off of this floppy, because it is a valid DOS 3.31. So here we are booting up, booting the OS, so there was no C drive, there was no XTID, no compact flash. We are actually booted up on drive A. So this is great. We could put this in a retro computer with no floppy drive, with no hard drive, with no storage media at all, and we could boot off of the Raspberry Pi mounted floppy. So I think this is pretty versatile. I think it's going to help me a lot in getting images from my Windows box onto my retro computers without having to shuffle compact flash back and forth. So it's also going to help me experiment with other boot disks, because it's very easy just to make a boot image and serve it to the retro computer rather than actually having to burn onto a floppy and bring the floppy over. So you might be wondering, this is a Raspberry Pi W wireless, and I've mounted it to an ISA card, and we're typically going to be sticking it inside of metal computer cases. The previous one I demoed was my nice acrylic one. It's not going to block any Wi-Fi, but something made out of metal could very well block some Wi-Fi. This is an IBM 5150. It's got a lot of metal to it. Basically the whole top, bottom, back, front is covered with metal. The only thing that's not covered is the disk drives. So let's boot it up. You can see there's no floppies inserted. And there it is booted up. There's our Champions of Kryn disk. I don't know if Champions of Kryn will actually run on this. We were able to mount the floppy. We're able to communicate with the Pi. Everything is working fine, even in the metal case. And this is on actual period accurate hardware. This is the Champions of Kryn floppy, but I'm not going to actually start Champions of Kryn. This thing has a monochrome display adapter. I don't know if it'll actually play the game on that adapter. Thank you for watching my video. Please visit my website at www.smbaker.com for more electronics projects and sandrail stuff. Bye.